We start off with a question, of course, because we're almost at lunch and everybody has seen a lot of presentations, and to keep you sharp, every good presentation needs to do something with questions. So we have a question. Who knows what this is? Earth. I hear some good answers. This is Neptune. Correct. So it's one of a few planets. We also have here a few planets. Does someone know why this order is in the planets as it is on the screen? Alphabetical. Yeah, that's true. So this is the easy one. And now we have another one, and that's the second one. Does someone know the size? Oh wow, you're much better at this than I am. I actually had to go to Wikipedia to look this up. So I had to learn something first. I had to learn about the sizes of the planets. And when I knew a little bit about the size of the planets, I was able to rank the planets in the order of their size. Well, this is a little bit of what we're going to talk about today. We're going to talk about learning. And when we have learned enough, we're going to do ranking. And we're going to do that in context of search. This is me. I am Jettro Coenradie. I am a fellow at Luminous. I do a lot with search, Elasticsearch, and I like to experiment with machine learning, and I have Twitter and LinkedIn and those kind of things.
My name is Byron Voorbach. I also work for Luminous, but I'm a search and data engineer, and I focus mostly on Elasticsearch at the moment, building, creating, optimizing search engines. And you can also find my stuff on Twitter, LinkedIn, etc. if you want.
Okay, so when talking about search and about ranking, it's always good, of course, to have some kind of context, because you can do search in like all over the place. So we're going to talk about search in e-commerce and about ranking in e-commerce. So imagine this, you're at the beginning of the year and you had Christmas and you're going to think about your next new year, and you see that you're going to do some presentations and you think about, I want to have a cool gadget for myself. So I thought about it and I wanted to have this because I saw this somewhere at a TEDx and I thought it was really cool that you could just point at your screen and then you can highlight the screen. Well, nowadays I think I'm not the only one anymore who thinks it's cool, because I think almost all the presenters have this gadget. So it's not that special anymore. But still, at the beginning of the year, for me, it was really special. So I went to a website, Amazon, and I could find it there. Well, it's on discount these days, so it's a little bit cheaper than it was when I was looking at it. But we're Dutch, so we're trying out different websites to see if we can find it cheaper. So I went to Coolblue, and yes, there it is again. It's my cool presenter. And well, let's try another one, and then we have bol.com. And oh, it's not there. So what happens? Well, I happen to know someone who's working on the search engine for Bol. So maybe he can explain us a little bit more about why this happens.
Well, the product is actually at bol.com. It's just not on the first list. Well, we can't see it here right now. So if we refine our search a bit more and add Logitech, we can actually see that Bol has the product. But if we go one slide back, what you can notice about this page is that a lot of the products that are on top have a really low price. So probably the people that come to bol.com don't have as much money to spend as Jettro when they want to buy a presenter. The thing is, what you see on websites when you search, you can always sort on a certain sort order, but the most default one is relevance. What is relevance? What does it mean? How can we influence it? And why is it important? It's important to think about relevance because products that get shown on top are tend to be more likely clicked. As you can see, the difference between a product on the first slot or on the fifth, the difference with the click-through rate is pretty high. So it's important to think about relevance and how you can adjust it to make a better customer experience. Since we want to show you something in a demo, we made this nice playground area where we indexed a lot of games from the PlayStation Store. And we made our own little web shop, which we can search in. So let's search for...
What do you want to search for?
Let's say Call of Duty. Any Call of Duty gamers out here? None?
Hey.
Any gamers at all in here? There are some gamers. Okay, cool. So, as you can see, we can search. We'll find the much older ones on top. But if we scroll down a bit,
I guess nobody knows then that this is the one that we want to have.
no. So maybe we should search on something else.
Yeah, let's try another one.
This time you can choose.
Maybe soccer games? Anyone? No? Ooh, tough crowd.
Yeah, tough crowd indeed.
Well, then just look at the pictures. That's, we've got Ronaldo and Messi.
The thing is, we can scroll through the site. We have pagination. You can click on more info. You get some more info about the games, and you can add them to a cart and you can buy them. So we have this small demo environment in which we actually want to improve some of these search results. Because if you search for FIFA, you want to have the latest FIFA. If you want to search on Call of Duty, you probably want to have ones on top that actually get bought most, or maybe get clicked the most, or maybe get views the most. So that's what we're going to be using today to improve. But how? Let's first answer another question. How do we get from Call of Duty to a list of games? Meet Elasticsearch. Can I see a show of hands of how many people know Elasticsearch?
Ah,
not so tough crowd
just
anymore.
asking the right questions, that's fine.
How many of you use it daily? Ah, still quite some. Nice. Just quickly going to go over Elasticsearch for the people that didn't show, or didn't put up their hands. Elasticsearch is a distributed search engine in which you can index JSON documents and query on with JSON language. What happens is you index documents, documents get analyzed, and the terms that you can search on later are getting stored in the inverted index. Same time, you want to query those documents, queries get analyzed, and you get your documents back. So let's just go over quickly what the inverted index is. Let's say we're going to index a few documents, for instance, FIFA. Elasticsearch analyzes this document and stores it in a column. So we have FIFA as a term with the linked doc ID where the original document ID was, plus the term frequency. Start adding more data, for instance, Call of Duty again, and we see that new terms get added to the inverted index. As soon as the term occurs that for the second time in the inverted index, the extra doc ID gets added and the term frequency gets increased. While this happens, continues on, the more and more you add data. This is an example of what a document looks like in our current index. So we have a few fields, we have a title, we have a description, we have a rating, number of ratings, and we'll be using this data later to improve our search. This is an example of a query that we're using. Right now, if you search, we just do a multi-match for Call of Duty on the title and the description field. Naturally, when you search in Elastic, it will just return some documents, and it will have them in a certain order. A ranking algorithm is applied to those documents, which makes sure that the most relevant document is on top. But what is this ranking algorithm underneath? It's BM25. Does everyone here know what BM25 is? Some people. Okay, that's a better one then. So this may look a bit scary at first, but it can be broken down into small components which are more graspable. In essence, the score of each document is calculated by having a TF norm versus the IDF. The IDF stands for the inverse document frequency. It actually means that the more a term occurs in the whole corpus, the lower a score will be. So the amount of doc frequency that a certain term occurs in makes a certain other document less in score. The second part is the TF norm. The more a term occurs inside a document, the more important it is. So if there's a lot of references about Call of Duty in the information field, that product will be on top compared to one that only has one reference to it. And the last bit is about the field length. So if you have a match in a title field, then that's probably more important than in a super long information field. Those are the small components that make up the current scoring algorithm. Next to having that scoring algorithm done by Elastic, we maybe want to influence it, because we know up front that certain fields are more important than others. So what you can do is use something called field-centric boosting, where we can just say a match in title is twice as important as the one in the information field. Another way to do this is using a function score query, where we can apply a function to the number of ratings. So we want to increase the score based on a function that we apply with the number of ratings that are given to a certain document. So Call of Duty that people like more will be boosted higher. Another form of function scoring is a decay function, where you can say, for instance, on release date, everything that's older than a certain year or year from now will be scored less because we want to promote new games. Oh, one back. One of the downsides of this, if you think back about the boost on 2, is that you don't know upfront if the title field is twice as important or maybe 5 times as important. And that can be pretty hard modifying those boosting values. Well, luckily, there's one other thing that you can do to improve this. And there Jettro will talk about.
Yeah, at least I will try. So, meet learning to rank. Byron has showed us that there is quite some extensive ways in Elasticsearch already that you can use to change the order of your documents. So you can use like boosting in fields that he showed and decay functions, and this is all interesting, but you have to explicitly tell it to do that. So you have to find out or guess or try to get the right factors in, to come up with these right ratings and to see all these decays. Do we decay in a year or 2 years or in a month? Those are all choices that you can make. But still, it's a choice you have to make. You have to test it, of course, and it might be opinionated. You can do A/B tests to do stuff. But there's one other trick that we can also try, and that is to apply machine learning. So in this case, we're going to see if we can teach a model to optimize these parameters for us, so that we don't have to decide like this field is best if we boost it with 2, and it's best if we do a decay here. But now we just add a number of features to a model, and then we put in some test data, and then we try to come up with the best model to do this ranking for us. That's what we call learning to rank. If you want to know the exact same definition, it's on Wikipedia, so you can check it there as well. Let's do a short recap on machine learning, and in this case, supervised machine learning. What's supervised machine learning? With supervised machine learning, we have an input and we have labeled output. So we have a test set or a learning set where we know that if we train the model, that we have the exact answers, and with the exact answers we can teach our model to do the predictions and to get in that same area, the same neighborhood of the answers. So a small example with the housing industry. So we have, in this case, a training set of 3 items, and there's 2 features in here. There's the number of rooms and the amount of square footage. And based on these 2 features, we try to predict the selling price of the house. We have 3 examples with the labeled output. So this first house was sold by 200,000 euros, which I don't think was in a very big city, because these days 4 rooms in Amsterdam, for instance, would be slightly more than 200K, I think. And we have the 6 bedrooms and even a very big 3 rooms house. Now we would pick up this data, put it into a model, train the model, and with the model we try to predict the selling price. But we have the actual price. So now we can calculate the error. And with this error, we are going to tune the parameters a little bit different, train the model again, and predict again, and see if our predictions are getting closer to the actual labeled output. And when we're close enough, we feel that we have a trained model, and then we have houses that don't have a labeled output, and then we can really do predictions on these houses like, oh, okay, so if this is the square footage and this is the amount of rooms, then you should try to sell it for this amount of money. Well, that's not really about search. So is this also possible in search? Well, with search, our input could be the query that we do. And based on the query that you execute, we can extract some features, which we will see later on. And then we put this into a model. And on the right side, we have at the Y, we have the labeled output. So someone has created a list. So if you search for query 1, then the outcome should be 5 documents in this order, like 5, 15, 67, 3, and 17. In the one that appears here, this is the prediction. So we have trained our model, and this is the predicted order. So if we look at the blue ones, the top one, you see that the first item was okay. We predict the right item, but the second item, it actually should be the 4th. So there is an error between what we predict and what we would like to have. So we can do the same thing. We have this error, and we put it back into the model, change the parameters a little bit, and try it again. Clear so far? Okay. So how do we calculate these errors? There's a number of ways you can do that. One is using binary relevance. And with binary relevance, what we just say is, if the document is relevant, then it's okay. And then we go through the list and we say, okay, the first item is relevant, check. The third item is relevant, check. And the fourth item is relevant, check. And then we can calculate the error margin, which we will see later on with an example. Then there is something we call the graded relevance. In this case, we don't say it's relevant or not. We say it's more or less relevant on a grade. So we could say, like, from a scale from 0 to 4, if it's 4, it's completely relevant. And if it's 0, it's not relevant at all. And in between, it becomes a little bit relevant. And of course, yeah, you can train your model in a little bit different way. And then there's also a thing that we call graded relevance, and then the cascade-based. And with the cascade-based, we could take multiple inputs from the user. So we can actually say, like, okay, if I have 5 items and the third item becomes relevant, then most likely the first 2 items were not relevant at all. And that's another way of looking at it. So to come up with an example, if we look for FIFA, then we predict this order. And this is the binary relevance. Any colorblind people here? Last time I had one and I said the green one is okay and the orange one is not okay, but he couldn't see. So I don't see hands, so just take it that the green ones are okay, so number 1, 3, and 5, and the other ones are not okay. When we calculate the average precision here, if we do it for the first step, it would be 1. So this is okay. For the second one, we don't try it because it was not relevant. Then for the third one we calculated, it's now 2 out of 3 that are relevant, so it's 0.67. And then with the fifth one, it's 3 out of 5, which is 0.6. And then we could calculate the mean average precision, which would be 0.76. So this would be one of the ways that you can calculate the error between the predicted list, the order that we get back, and the actual that we decided somehow that would be the best fit. Well, the same you could do for the graded relevance. Now they are all green, but we say there is a grade in there. So the top one has a relevance of 3, which is, well, it's okay. It's really relevant, but it could be even better, which is the third one, which has a relevance of 4. So this is what we predict. Then we can calculate the discount cumulative gain, and we use these grades that are in the end there, and then we calculate in the end with a formula that it's 8.07. The problem with this is that it is hard to compare. So if we do a second query, which has like 7, 8, or 9 results, then the DCG value always becomes bigger. Well, it potentially becomes a lot bigger because you just add up. And that's why they came up with something that we call the normalized DCG. And with the normalized DCG, we normalize the DCG value with the maximum possible DCG value. And with that way, you always get a score between 0 and 1. So the higher the score it is, the closer you get to the actual result, so it's better. Just to recap here, we have the input and the labeled output. We put it into the model. The model has an algorithm and some parameters. Using this algorithm and parameters, we do a prediction. We calculate the error using one of these cost functions that we discussed before, and then we optimize the parameters and go over it again. Okay, so how do we use this in Elasticsearch? These are the steps we have to take. First, we have to create this judgment list. This is the list with the 5 items that we are saying, like, this is the correct order. Then we have to define features for the model. We have to log these features, and then we train and test the model. We deploy it to Elasticsearch, and we can do it again in another way. Try it, change it, and try it again. First, the judgment list. We have to somehow obtain this list, this labeled data, which is the correct or the optimum list that we get back. You can do that using an expert panel. So you just let, this is the way, for instance, that Google uses it a lot. You just set a lot of people in a room, And they start using it, they start entering search terms, and then they look at the results and they say, okay, this first result is a 4, this second result is a 2, this third result is a 5. This is what we call an expert panel. The problem with this is that it's error prone. It can easily become opinionated. So what one person would say, this is a 4, another person could say this is a 2, depending on your context or your opinion. To prove that, we want to do a small experiment. We're going to present you a few pictures, and you have to tell us if it's a pet or not. So what about this one? Is this a pet? This is actually my dog. So this is a pet. And this. Is this a pet? Hakan says it's yes. Blame you. Of course not. I mean, we're just friends, but I wouldn't recall him as my pet. That would be a bit stupid. Yeah. Now this one. Who would say this is a pet? I see a few hands. Not that many. It's a bit scary, especially on the big screen. It looks like it's almost coming at you. But this is debatable. So you have to give persons a context to choose whether this would be a pet. I mean, you pointed your head, so if I would ask you, would say, yeah, this is a pet, and number 4, this is a real good pet. And then someone else would say, no, 0, definitely not. So you get this difference. So we could, for instance, when we ask people, say, would this be an animal that most common people would like to have in their home? Well, it's still difficult because someone loves dogs and the other one loves cats, but let's just say, like, okay, this could be a context that you could give. Well, if this is too hard because it's too time-consuming or too error-prone, we can also use another mechanism which we call implicit feedback. Here we log the user behavior and we try to learn from the user behavior and decide whether people, if they click on something, that it will be relevant or not. It's also a bit difficult because a click doesn't really always mean that it's relevant. If you get back a list of results, you click the first item, you see, oh no, this is not what I want. You go back and you click the second item. Was this first item relevant or not? Well, if you just use clicks, you would say yes. But if you would use other mechanisms, you could say no. So this is also something that you have to think about. Well, using this implicit feedback, we can use it in 2 ways. The first way is that we use it more as a signal, as a feature in our model. That's the first way we're going to demonstrate. And we can also use it to create this judgment list. And that's what we, in the end, are going to do.
All right. So we had some of the theory now. Let's go into the good stuff. We're going to be using the Learning to Rank plugin made by Open Source Connections. It's an Elasticsearch plugin that you can just install, which you have to do some pre-work for. But then it's fairly easy to use. So we'll just be going through the steps in order how to use this yourself. So we chose to do be our own expert panel. So we made a judgment list based on the searches that we could do in our engine. So up top, you see QID 1 till 6. Those are the queries that we've been ranking. On the left, you can see the numbers of relevance, so the graded relevance that we gave. So for QID 1 on the top hit, we gave it a 4 because we searched for FIFA, if you see on top QID 1, and the returned result was FIFA 18. So that's a good hit. So in the second column, you list down all the QIDs that you want to grade. Third, you add the document IDs, and as fourth, you add the titles. So this is the format of the file that is needed in order to start training your model. So we have that. We have our judgment list. The next step would be to define features. As we saw, features are characteristics about your documents. So we want to create some in order to train the model later on. So there's 2 ways of doing this. You can either use some raw term statistics inside Elasticsearch itself, which is the document frequency or the total term frequency. You can also use min, max, and sum. And the other way is by defining Elasticsearch queries, which is what we'll be using today. So what does this look like? So in total, we're going to be defining 6 features, 6 important aspects of our document that we think would be good to improve on. So the first one is a match on title, because the title is something descriptive. That's what people will be looking for, so it's a good feature for our model. The second one is a search on description. Then we have a third one. This is the field value factor I've shown before. We're going to be using the rating of a document as input for the model. Next one is the release date. So we think it's important that users, or that our model distinguishes between older games and newer games. Next one, this one looks a bit tougher, but what it does underwater is take the amount of clicks on add to basket into account, based on the search term that was used when it was clicked on that basket. Next one looks the same, but we'll be using clicks also as a feature. So we have 6 features now that we went through that we'll be supplying to the model. So the next step after defining the features, we need to actually log the features. So we need to run our queries and see what these features, what the results for that was. So again, a new form of a new file. On the left, you see the graded relevance from the previous file, plus the query ID that it belonged to. And then we'll be logging our 6 features in a row. So the first feature, if you remember, was the search on title. You can see for the top hit, for the first one in the top, it says 7.791, etc. That is the actual BM25 score. So it's the Lucene underlying score that gets calculated. And we log that here. The second row is a match on description. Third one was the rating. We have ratings from 0 to 5. And you can see that some of them are 4, 4.5, and there's a 0 in there as well somewhere. The next one is release date. As you can see, the top one has a score of 0.99. It must be a really new product. We can search for FIFA. It's on the top right. It says at the end FIFA, so we know that that's probably the last one that came out. Next are the basket clicks. We can see that there's a lot of zeros, meaning that those products have not been clicked on for add to basket, but also the same for clicks. So now we logged our features. Now we need to train and test the model. We're making use of RankedLip. RankedLip is a Java library that you can use to train and test your model. You can specify separate train, validation, and test sets. And it can normalize feature sets for you if you're not able to normalize them yourself, if you cannot access the data yourself. So RankedLip comes with quite some models. We won't be using all of them. I won't be covering all of them. But in the end, we'll be showing that we'll be using one to actually improve the search in the end. So Jettro talked before about calculating the error, or the cost function. There are some evaluation metrics inside RankedLip that you can use. And we'll be using the ERR at the end, the last one. But I will touch a bit on that later. So we trained and tested our model, and we actually made a nice overview of showing which metric with which model gave the best result. As you can see, there is rank boost on top, which has a couple of 1s. A score of 1, you could think like the closer you get to 1, the better, but having actual 1 is not so good. It mostly means that your model overfits. And overfitting means that you have too many features and probably not enough data to train your model. So the model is perfect directly. Well, perfect directly never works. We'll be using this one. So we'll be using lambda mart in combination with ERR in order to train and test our model, because it gives the best score. So now we have our model. Now we need to actually deploy it. So we need to upload the model into Elasticsearch to the plugin so we can use that during our queries. Using the plugin, I will show that in the next slide what it looks like. But what you can do is you can rescore the top X amount of documents that you want to improve the relevance for. You normally don't do this with the whole set, but you just say, okay, the top 100 results, those I want to sort based on my model. So this is what it looks like. Again, we have our multi-match query on title and description, but now there's a second block added to the Elasticsearch query called rescore, where we say for the window size of 100, so the top 100 results, we want to reorder those based on our model. The model name is test6, and why that is we'll show later. It's not really descriptive. But we're going to be feeding the same search term into the model, so Call of Duty. Let's see how that works out.
Okay. So first we have to tell our application to use the query now for learning to rank. We have this Swagger UI that we can just say, okay, use LTR now. And it should have worked. We go back to this one. And you can actually watch the logos change when we rerun this query. So now you see that Call of Duty is both on top. So we are satisfied because we've got our game and we found it and we can now buy it. Well, for the FIFA part, let's check this one. If that's, okay, this is kind of okay. FIFA 19 is at first, but then we've got FIFA 18. I guess there's someone who likes this better than the new one, and then there's the more expensive 19 version over here. So it does influence it. It might not be optimal yet, but we're getting there. Any more you want to show? No? Okay, this was my call again. So we now discussed this, the judgment list that we as expert created and trained our model, and we saw that it kind of worked. It might need some tuning, maybe some more test data, maybe some better judges, could also be. But we also have our users. So our users are using the website, they are clicking, they are buying stuff, and maybe we can learn more from that as well. We already used the clicks and the basket clicks as features in the model, but maybe we can also use it to improve our judgment list. So maybe we can use the actual clicks to create a judgment list. Well, there's a number of ways that you can do that. That's what we call click models. There is this random click model. And with there, you say just say like every click is possible, so everybody can click everywhere. Well, we discussed already the click-through rate, where studies have shown that people tend to click the first item the most, and then the second, and the third, and the fourth. These days, it already changes a little bit because we now have often rows, just like we have with products. So it's more like the first row gets clicks the most and not necessarily the first item. But this is research that you can do. So you have to go to the second model, the click-through rate model. And with the click-through rate model, you just take into consideration that we expect the first row to be clicked more often than the others. So if one item of the second row is clicked a lot more, then we're probably off in our relevance, and then we have to do something else. Then there's this cascade model. That we discussed a little bit as well before, and there we just say if a user clicks, and we just consider every click, then if he clicks the third item, it also says a little bit about the first two items. We would say that the first two items were not relevant. And then at the final one, which we call the dynamic Bayesian network model, with this version we take into consideration all the clicks that a user does. So if a user clicks 3 times, and then leaves, well, we take it that he was satisfied when he left, and then it must be the third item that was actually satisfying him. Yeah, I see nodding, but true, it's an assumption. It's not always right, but we just, for most of the clicks, we just assume that it's that case. And then we could also say that the first 2 items are likely less relevant. Well, then you can use this nice diagram to show this. The first dots with the E in there, they say that a user examines a URL. And then we've got on the left, we got the one with the A, which says that he was attracted by the URL. And if a user examines a URL and he is attracted, then he clicks. Well, if he clicks on an item and he is satisfied, which is with the S, then he leaves. And if he was not satisfied, he's going to examine the following URL. Well, this is the assumption of the model, and then the model will, in the end, try to come up with good factors for the A and the small a and the small s, and then we have trained the model, and then we can use the clicks to actually come up with a predicted judgment list. So what did we do to accomplish this? We have our application, and we register all the clicks using the logs. Then we use logstash to put all the clicks into Elasticsearch. And then in our application, which is the web shop, I'm not saying that in production you would usually do this, but for now we just did it. We just got an endpoint in there that would export this data into a structure that we need for var epsilon. And var epsilon is again a library where we can just put in the data and then it comes out with a judgment list. And then we have to do some Python magic to come up to change the format of that judgment list that var epsilon delivers to be able to send it back to our plugin, the Learning to Rank plugin. we store it into Elasticsearch, and we have a trained new model. This is the format of the file that the application exposes. So we just say all the clicks are in here based on search term. If you would per line take out what's really important, we have this query ID, we have the query text, in this case Call of Duty, we have all the document IDs that were on the screen, and we have the ones that were clicked. So in this case there were 3 clicks, indicated with the 1 in there. Well, then we store this into var epsilon, and it comes out with the file format in the middle, which is not the same as we want it to be. So we take the Python code, and now on the right side you see that this is the format that Byron has shown to you as well. Only this time it's not created by us, but this time it's generated by the machine learned var epsilon. Okay, now we're going to see if this helps and gives us better results. So this is the Python scripts that we use to train the model. In this line, it's not really, but maybe it should be visible. This is the ecom judgments file is our own, the one that we created. Now I'm going to comment this one, and we're going to use this one, which is the implicit judgments. This is the file we actually generated with var epsilon. I'm not going to all the stages, but we're just doing the training of the model. So I'm going to run this. And now you see that it iterates for it, so it will train all the different models. And you see all the iterations that it does. It calculates the error scores, and each time it's on a certain threshold, or for some models it's just a number of iterations. So sometimes you say we continue until the error margin doesn't change more than like 0.1. Others say just do it 100 times, and that's for each model that can be different. Now it's done, and it has pushed the models into Elasticsearch. So if we would now go back into the sample and we search again, then we see that based on clicks, okay, for FIFA, we found better results than we did when we had our judgment list. And I am afraid that in this case, if I go back here, then it's slightly off. Okay, so what can we learn from this? It's not easy. And of course you need data, because as you saw in the file that Byron showed, we were just clicking on a few of the items. So what did we do? We created this file ourselves on my laptop, so there's not a lot of data in there. But it's something that, yeah, if you have more data, then of course you hope that there will be a better trained model in there. And yeah, that's it. So, are there questions? I see a hand in the back.
Yeah, I was wondering how the model is updated.
So how the model is updated, you mean in Elasticsearch?
Yeah.
Yeah, oh, that's the Python script that I run. Yeah. There is an endpoint in Elasticsearch. That's the plugin, the Learning to Rank plugin is supplying. And we just send the trained model to that endpoint.
But the trained model is a new version of the model.
Yeah.
How does that work?
It overrides the old one.
Yeah, so you just train that offline, and then you upload it into the plugin to have a new updated model. So it doesn't do automatically updates, or you cannot put a feedback loop in there to automatically do that. So
that was the test_6 that you saw. The Python scripts used that name to put it into Elasticsearch. And that's why test 1, because I think we upload 10 different models. Test 0 to 10, test 9. Other questions? Yes?
If you have someone tampering with your search results, like a vendor of a game who's making lots of clicks for a certain title, how can you correct it afterwards?
Yeah, of course we have a filter for that. So we just take it out if people, yeah, I mean this is cleaning your data.
Yeah.
Yeah, so I mean you can use IP addresses, you can use the session ID. What we for instance do is that if you do a query, we get back a session ID for that query. And the moment that you keep clicking, then it keeps the same session ID, and we will notice. So in the end, we don't take the amount of clicks, but we actually take the amount of clicks per session. But it's, I mean, yeah, no, because if you just kept on opening your browser, search again, and then of course you could still fool it, but then we have to make smarter solutions for the data cleaning. Yeah.
Okay.
Other questions? Yes?
To use an actual product board and trace it back to the search, or and use that as data for the model?
It's not really clear what you mean.
If you use the product being bought in the shop and trace it back to the search they used to get there and use that as a model?
That's sort of what we're doing. So what I showed before is that you would do a search on a certain keyword, and there would take the basket clicks. So for instance, you can use those basket clicks and the normal clicks. We store that together with the original search term that was used when to click on that certain document. So in the end, you get, for each document, you get a whole list. Okay, these were the clicks, and this was the search term that was used to get to this product. So we're using that as information in order to train the model already.
Yeah, so it's not that we store the clicks per term that you search on.
Yeah, because otherwise, yeah, you have a huge amount of clicks, and then products will be boosted to top that just have a high amount of clicks, but are unrelated to the search term. So that's why we store the combination of the search term and the click, and we increment the click if more people get to that product with the same search term.
Yeah, and with the var epsilon library, it even takes into consideration where in the results you got back. So if you're number 1 and you got a click, it does a different thing than your number 8 and you got a click. Yeah.
I'm also curious if you can do something that if you click to get more details on something, but that in the end you don't continue with that, can you then ignore it and place it lower in the list? Because that actually shows like this appears to be a good hit, but actually it's totally there.
That's a good question. So the question is if we can use more information actually. So if you're just going for the details, but you don't store it in your basket, for instance, then you could give it a penalty. Yes, of course you can do that. That's something that you can decide. You can also train your model that he can decide. So maybe but the fact that when you decide that someone is satisfied, that's the most interesting bit. You could say if he's looking at the details for more than 10 seconds, and if he's looking like less than 1 second, we can even give it a penalty, because then most likely he didn't like it at all. So that's definitely true. It's possible, yeah.
How do you choose what kind of parameters you're going to use in the model?
The features, you mean? Or?
Of what kind of features?
Yeah.
Because it's easier to reflect on the housing situation. If you do it with the housing situation and you start to input a feature for location, for example, you can get completely different results because the house is somewhere in the north of Groningen instead of central Amsterdam. How do you choose which features are relevant enough?
Good question. I think that is one of the hardest things when you start out, is choosing what you want to use as a feature. So we right now we actually use quite some. So we have quite some different features mixed up. The hard thing about it is that you cannot really tell afterwards which feature made a certain search result. But yeah, for choosing them,
Testing.
yeah.
I mean, that's I think the whole data science job, that you, of course, with some domain knowledge. I mean, if you got to go start talking to real estate people, then they will tell you that location of the house is really important, and maybe that if there is parking spots in front of the door, that's also an important characteristic. And you don't want to get like 1,000 features, because then it's hard to train, and then not every house has that characteristic, so it's really hard to do predictions. So you have to find a balance in there, and it's I mean, it's, yeah, I think that's the whole thing. If you want to get good at it, then you should talk to the right people and with domain knowledge, learn about it, and then yeah, and experiment a lot, try it out. Yeah.
And I think when you're experimenting, it could be wise to start with low granularity fields, because there's not so much difference in the results then. So it's either go left or go right. Like if it's more binary, then you can also more easily explain afterwards if the model is doing a good job or not.
See a question on top.
Do you take document similarity into account? Like for instance, you were predicting on the basis of a FIFA query term, but also some other soccer games would show up. And which the name FIFA did not appear. I think Elasticsearch by itself cannot produce that, right?
The thing is that you didn't see the complete description. So
But even assuming that FIFA doesn't appear in the description, you might still want them to show up based on similarity between other soccer games.
yeah, there's features in Elastic that can do more like this, like that. But that is not what we're using now. So now we didn't do anything with synonyms or enriching the documents to have every soccer game come up when you search for FIFA, for instance.
You could also use synonyms for that, of course.
Like a lot of things, if you want to improve your search, it's easier just to stick with the Elasticsearch parts where you can already change things instead of trying to do that with the model. Because a lot of the things that you want, you can actually already do. But one of the things why LTR is interesting is because you want to re-rank in a certain order. So it's not so much about matching, just finding documents. It's more about ranking and changing the order.
Could you generate a model out of the descriptions? Or a model feature list? Like take the content, the actual content, and make the filters out of that?
Not really sure if I understand you correctly, but we are already using the description field in the model, but I think you mean something else.
Yes.
Yeah, I'm not aware if we can, I mean, it's not that we do some dynamic feature composition out of the text or something. That's not what we do. So we create the features ourselves, and then we train the model based on these features. It's not that we do feature engineering dynamically out of content. That's not this area, at least.
And it's also not possible with the framework?
Not with this library, no. I think then you have to go more into things like TensorFlow and do things like classification. But that's another area. Then you're more into processing your text and not necessarily in ranking the products. Other questions? Okay, well, then we're done. Thank you very much.